All right. Hi, everyone. Good evening. I hope you've been enjoying the talk so far, but even more so, I hope you have the energy for just one last one. We're going to be spinning a yarn on an open source project called Atomic Red Team and how we can build a basic, scalable testing environment for it. All right. So first, who am I? Hi, my name's Tess. Yeah, you heard the introduction, but in case you would like to know, here's some of the stuff that I've done. I really like to raise lots of animals and push permaculture because it's important. And I collect hardware and technical books in my spare time. And of course, I spin, knit, and crochet. It's what I do. So, what is Atomic Red Team? That's what we're here for, right? It's magic. It's a hyper flexible library of tests for all purposes, but especially to test detectors and logging capabilities. It can be run on the local machine or it can be run remotely, which is awesome for big environments or for those who just want to try it on a single VM. You can just run it on one VM. It's really cool. It's currently in the top 20 of the Open Source Security Index, so it's got mad street cred. And if that wasn't enough for you, it's used by a lot of companies as a starting point to make very big products and tools. It's pretty neat. So why Atomic Red Team? It's free. Yes, free. It's an open source solution, so it receives regular updates from viewers like you, and possibly also you someday, maybe. We all like free and supported stuff. It's also got a feature for easy cleanup. It can fetch dependencies. Many tests also have cleanup commands available to return the system to its original state after you're done testing. That's pretty cool. It works on a lot of different operating systems. That's right. It can run on pretty much any operating system, including container-specific and cloud-based operating systems. This is a really big advantage as many testing frameworks can miss environment-specific techniques, especially things like living off the land and specific behavior relating to logging. It's scalable. Your environment does not have to include a scene. This is a big deal to note in. You don't have to add in a scene for this. It can just be your testing system if you want. Because you can run things locally, you don't have to worry about building out a ton of stuff if you don't have the desire, resources, or time. You can use the built-in logging system in your operating system. There's tests for almost any situation you can imagine. Being regularly updated by a community and based on a framework like Attack Framework has its perks. New tests are created every month, and again, you can contribute too. And it can make your detection dreams come true. Detectors are important, and striking the right balance between true and false, positives and negatives, is extremely difficult. Atomic tests emulate nasty stuff that you might see in a production environment, so you don't have to worry about catching it when it does show up. So here's what we're doing. We're going to do some image install networking, same configuration, agent configuration, different options for tests, breaking down the alerts and how this works IRL. But just an FYI, we're not doing this live. I'm not enough of a glutton for punishment to do it live because I'm really good at unwillingly figuring out every single way that something can go wrong. And yes, it's not going to be the whole gambit of install. You're not going to be witnessing me go through the individual steps of every install. A lot of this has very good documentation, and I will link to that at the end. We're going to be very specifically configuring Security Onion and a Windows testing PM. And we will be emulating an actual threat today. I wrote up an article on Bootloader that will be out soon, maybe, we'll see. And I compiled some tests together in YAML for that, but we're going to be executing one of those tests out of that. Then we're going to sift through the alerts together and see how the tests influence your logging. And finally, we'll talk a little bit about how you use the experience that you gained in the production and, how you use the experience that you've gained from this in a production environment and how you can test in production. Scalability is key. So with that setup. So this is kind of what it's going to look like a little bit on a very basic level, right? You can exchange out pretty much any of these for an item of your choosing if you don't like this virtualization solution, if you want something different for a firewall, whatever. But the entire idea here is to make it so that you can swap, you can scale, you can kind of do anything. So we'll be using VirtualBox, free, open source, lots of good documentation. Can be a little finicky, but it's good enough for this. If you have sense, If you already have VMs, this will help us create a box around your testing environment so you don't accidentally mess with other VMs that you care about. It's another open source solution, this time a router and firewall that can be configured via a web interface. And then we're going to be setting up a Windows image with Atomic. You can use any image you'd like to work with here. There are images for older versions of Windows on Web Archive. The tests you'll run might change based on operating system, though, so keep that in mind. We'll be running the tests locally on the operating system because it keeps things a little bit less complicated. There's Security Onion. This is our security information and event management tool, and it will pull information from our testing target via agent and tell us all about what's going on with it. Once again, this is why it's really nice to have a Cordon network. This little guy can see all the stuff on its network segment if you want to configure it for that. So you want as little there as possible. You don't want to be digging through logs forever. And special mention to Splunk Attack Range. If you want a ready-made tool that can spin up VMs, test things, and auto-forward your logs to a configured instance, the lovely folks at Splunk do have your back. They're pretty cool. We're doing the more built-out thing because I want you guys to make sure that you know the ins and outs of how atomic testing works. Attack Range runs this a little bit more behind the scenes, so not really for our purposes today, just for your knowledge. All right, so our aim here, simple, flexible. This setup works for almost any testing. Build yourself an internal LAN. Oh, wait. There it is. Build yourself an internal LAN classified in VirtualBox as an internal network adapter, and that is going to go on your pfSense router and firewall. Your pfSense firewall will be the one to provision this for the rest of your network. So it will have two virtual network interfaces. One that provides a network connection, pulls that in. One that provides a network connection, that's going to be the internal LAN, and then one that pulls it in, a NAT link. That connects through the VirtualBox networking engine to the internet. One of the beauties of pfSense itself is that you don't really need to do a ton after initial install, if you don't want to. But you do need the pfSense virtual machine to be up if you want to run networking in your lab, because it's designed to be presiding over that internal LAN and provision out that connection to other machines. If you disconnect it, it breaks that link. You can access the pfSense web interface with any of your in-lab machines as you would with most regular firewalls at home. 192, 168, 1.1, everybody say it with me. You don't need to do much besides setting up a password, though. So when you're done there, make a note of the network details on your pfSense virtual machine, paste them in a notebook, write them down. You will need them. All right, Windows. I'm not going to go over how to install Windows with you. They make it pretty easy. But that being said, yeah, in your future test environment, you can totally use any operating system you want. It's just for Windows, this is going to be a little easier to talk about. It'll also be more interesting to see what we need to do to pull off these tests on a more modern operating system. As many of you may know, guided. In your network interfaces, you're going to add both your internal LAN and a host-only adapter, which will connect to your Security Onion instance for monitoring. Once it's set up, use the ipconfig command to get the IP address of your interfaces, write them down. Next is Security Onion. Security Onion can take a look at your local network and see all the nasty things going on inside it. When you set up this machine, you're going to have two interfaces connected to it, internal LAN, host-only adapter. The host-only adapter, once again, connected to your Windows operating system. And this will be sniffing traffic and pulling logs from that interface. While the host-only interface is not super necessary, it does make things easier as far as finding logs and pushing logs to Security Onion. The internal LAN interface allows you to access the internet and update sending your connection through your pfSense machine. So after you install Security Onion, make a note of your IP. Use the so-allow command. You can see it right there. And choose option B because we are going to be using log stash to ingest Windows logs and put in the IP to your internal LAN adapter from your Windows machine. This allows you to use the Security Onion web portal on your testing machine. All right, Security Onion configuration. We're getting a little further. You're going to update with soup, which is the most insanely well-named command of all time. It can't just be put on a VM and slapped in place. That's not how security onion works. So once you do that update, it will tell you, you're up to date, good to go. You can also check container status with SO-status, because this is basically an enormous cluster of Docker containers. So you want to make sure that everything's up and working before you start. It doesn't automatically pull logs from systems, so some configuration on the system to be monitored is going to be necessary. The image to the right is winlogbeat.yaml, a file that you'll be configuring on your Windows machine after you've downloaded the winlogbeat agent using the Security Onion install guide. This is a list of some of the events that we might forward. You'll put your Security Onion host-only interface IP in this file under log stash to forward logs to Security Onion. WinLogB. This is one of the worst setups that I have ever done because I didn't know how to read documentation. Do not run WinLogB setup. That attempts to set up indices on Security Onion. I probably spent several days on that because I can't read. It already has its own indices. Instead, you're going to be configuring program data elastic winlogbeat.yaml. Just configure it, start the service, set it to run on startup, and then you're going to add it to the firewall exclusion because you don't want firewall to get in the way of your logs. All right, and a side note, Sysmon is really nice. It's great for ingesting more system logs in more detail. There are several good guides for getting this configured out there. There is one in the Security Onion setup guide. Swift on Security's config is great, also mentioned in the Security Onion setup guide. And it pulls a lot more PowerShell info, which is really important for stuff like this. So once you let it sit a while, this is kind of what Security Onion is going to look like. Right there is a nice little dashboard with a lot of logs that are getting pulled in. You can see all of them. It's nice. It's got colors. And then right over there, you can see all your container statuses from running that SO-status. Everything's okay. Actually, everything's more than okay. It's shiny. All right, so enjoy this process. Seriously, learn about the new tools. Install what you'd like to install. Read that Security Onion wiki. It is so unbelievably worth it, I cannot describe it to you. Almost everything mentioned there is already activated and ready for you to play with, or only requires a few quick steps for you to do so. So without further ado, let's get testing. Yay. All right, let's get a look at what atomic tests are like. So we have our first test in the list here, and it has an explanation of what it does in the prettified format on the left, pulled from the atomic redteam.io site. On the right, we have the YAML file pulled from the atomic GitHub project. It's the same test. This should give you a better idea of the test's different pieces, some of our possible arguments, dependencies to be used, files to be pulled, and finally, how the test uses all those things in its commands. Either way is fine, but if you want to really deep dive and learn more about atomics, then the YAML is a fantastic resource. Okay, so let's try it. You can either copy directly from Atomic Test Markdown, what we just saw, or you can use a testing framework like Invoke Atomic, which automatically pulls and runs the test with its dependencies and then cleans up for you. It's quite nice, but if you're a beginner, well, you're probably not going to see what's going on behind the scenes, and that kind of sucks. You'll want to know what's going on. So we're going to be doing Atomic Red Team directly. Okay, so I told you we were going to be emulating an actual thread. That actual thread is bootloader. We're only going to be running one test today because we don't have time for more. This is going to be execution from a compressed file, T1027 under MITRE ATOMIC. So I made a script that just combines the dependencies, the test command, and the cleanup, named T1027.ps1. This script, I cannot describe to you how bad I am at PowerShell scripting. So there's like nothing else in there but the commands that you see in that screenshot right there. Like nothing else. And then I just ran it. That's it. I didn't do anything else. So what now? We've run something that should set off like a lot of alarm bells. The first time around, you might have trouble with Windows Defender. It might block things, but this can be a good thing if you're in a production environment. You know that at least Windows Defender is going to be a first line. However, we're going to keep going and turn off Defender because we want to test our detectors. For network tests, your firewall might block them. Same deal. Again, you should try it when Windows Firewall is on and off and look at the differences, see if it gets picked up or not. So let's find it in the logs. We're going to go into Security Onion. You can see the exact same thing in Windows Event Viewer. Remember, we're adjusting it from there. But you can search using the IP of the Windows machine on the host-only adapter. So here's what some of the logs look like. Excuse me. You can look in the Alerts, Hunt, or Cabana tabs. There will be several markers that can help you find this information quickly. The first is the name of the script. In this case, it's going to be t1027.ps1. You can search for that directly without any other arguments, and it should pull up these alerts. You can also use the machine IP address or name, the string PowerShell, or the user you executed it with. All these are fine. We'll probably lead you there. So this activity right here shows the execution of our script, the decompression of our file, and the execution and the fact that it triggered a process bypass because it was in a PowerShell script, again, can be important for writing detectors. It also shows the machine, the user, that's me, and the fact that it's in PowerShell. In other atomic tests, you might be searching for something different from this, perhaps network connections or executions using different programs. The important part to keep in mind is the pieces of a test that can help you identify its behavior and the detectors that would be needed to pick up on that. So what if there's no alert? Oops, it happens. And actually, that's a good thing. It means you found a blind spot in your detections or something isn't working properly. That's why we always, test. This playbook in the Security Onions Playbook tab, when installed, will communicate with the last alert, which is a built-in alerting system in Elasticsearch, and allows you to start seeing those alerts. So with all that said, why is this important? What have we learned? You just built an environment extremely similar to ones used in production instances, and in some cases, pretty much identical. You've tested a freely available detector and learned about what it actually did. You've learned about where everything is in a commonly available seam and whether your detectors are working properly. You've learned where to find additional detectors and where you can build them if you want to fill in the gaps, which is Playbook. It does have several features to actually build detectors from scratch. And you've learned about an excellent method of testing pretty much any detector you can think of, which is atomic red team. So what's that like IRL? Well, when I was working in an MDR, we had an extremely similar setup to this. We used a direct feed into Elastic from customer data lakes, just a big pool of logs, and then used Elastic to parse through information in Hunt. It looked a lot like this. All the pieces that you just did were split up, though, because it would be this process times 1,000 or 1,000,000. Dozens and dozens of customers, hundreds to thousands of machines to ingest from, an enormous array of different ingests from all sorts of products. It went far beyond WinLog Beat and into Google Cloud, Azure, endpoint detection solutions, the whole nine. We had to be flexible while maintaining data integrity from literally every news source. So that's what an MDR looks like IRL. What does an atomic deployment look like on a large scale? First, detectors don't tend to be directly provisioned into production. They tend to be tested first, hopefully. So new detections will be brought into a staging environment, and a fresh atomic test catering to that detection will be run. After that detection has been tested, confirmed working, it might be deployed into production and tuned to the liking of analysts and detection engineers, of course, to remove false positives. Then an entire gauntlet of regular atomic testing, usually scripted, so it doesn't have to be written out every single time, is scheduled and run to confirm that detections continue to work even with tuning. You want to make sure that your detections continue to work. So with that, take a look at those. There's some sources. They're very good for you. Now stick with me. Now that you've thoroughly exhausted your brain, let's get to spinning. Much more relaxing than this. All right. So I'm going to stop sharing here. Hello. And I'm going to swap cameras. All right. Hello. welcome to my spinning wheel. I'm kind of just going to show you what spinning is like and how it works. All right. So this, well, I named it. I'm sorry to say that that's kind of embarrassing, but I did. This one's name is Marigold. Ladybird is in the next room, and so is my dog. This is my second spinning wheel. Before I get into spinning on a spinning wheel first, though, I want to show you some pretty cool methods of spinning. All right, so here we have something called a spindle. This is a Turkish spindle. This looks kind of weird. And the average person would probably look at this and say, how does this make yarn, right? Well, it works the same way that a spinning wheel does, actually. It's kind of cool. So by simply adding twist to a lot of individual pieces of fiber, you can force them to bond together and interlock, kind of like, I don't know, like Velcro. Hi. And that process makes something significantly stronger as a whole than just the sum of its parts, right? So how this works is you twirl it. It's like a top, right? And I have some fiber attached, and it's just fluff, but as the twist from the spindle travels through the yarn to the fiber, it slowly begins to pull it all together, right? So Turkish spindles are pretty cool because you can easily disassemble them. You just push this piece through, and then these two pieces come out, and then you have something called a turtle, which is just a bunch of yarn that you can use to ply with. We'll get to that later, right? Now let me show you some of the yarn that I've already completed, actually yesterday. Don't ask how I found time. So a finished yarn can look something like this. This is a lot of it too. It might be a little lumpy and bumpy, like this is. This is by choice. I'm not this bad at spinning, I promise. But it has this sort of cohesive texture, and that's because it's made with two plies. So plies are made from singles, and singles are the main thing that is spun from fiber. When I'm here and I'm taking this raw fluff here, if I can grab it, we'll see. This fluff, right? This pulls apart pretty easily. Now, in order to get that to stay together, you might be tempted to just twirl it around your finger. And that gets a little bit better, right? But it's not perfect. And you don't really have the ability with your hands to quickly create a lot of yarn, right? You can't make it that much thinner. And yeah, it seriously takes forever. But spinning as a whole has been around since before documented history. It is something we straight up don't know when it was invented, because it's kind of always been around. So with that being said, we eventually got to the point of saying, how do we get this more production? How do we get this faster? How do we create more yarn with less effort? And this is the result. This is a Saxony style spinning wheel. There are earlier types of spinning wheels than this. One of the first is known as a charka, which was first developed in China and then popularized in India. I don't remember the exact century, but it was an extremely long time ago. But they all run off of the same principle. You have a wheel here, which is controlled by some treadles that my feet are moving right now. And
a drive band that connects into the whirls here. The whirls will take all of the energy created by this wheel and transfer it into these tiny little areas, right? So these tiny little grooves. And depending on the size of the groove, it'll make this whole piece rotate a certain number of times, right? So that being said, what I'm working with right now is called a 32-to-1 whirl. So for every one spin of this wheel, this spins 32 times. That's a lot. That's going to be 32 twists in your yarn every single time this moves. Now, you're going to want more twists for thinner yarn and fewer twists for bigger yarn. It's simply because you don't really like, I don't know, you don't need nearly as much for larger diameter. I'm trying to remember the words for that, but whatever. So with that, what's happening here is there's yarn coming out of a hole right here, right? And it's being pulled through onto the hooks here and then onto the bobbin. Now, the pull onto the bobbin is being done through this second strand on the drive band. This is all one big loop, right? It's just crossed over. And this second loop is slightly smaller, if I remember correctly. So as I start slowing down, it starts being the main one that's driving, and it starts pulling yarn in. So faster I go, the less it pulls. Now, what I'm making right now is a lace weight alpaca yarn, and I'm making a single, and I'm connecting it up right now. 1 second. So I'm going to get back to where I was. There we go. And then I'm connecting my fluff. And I'm going to do something called a long draw, where I simply draw back my fluff and then slowly, I lost it, and slowly expand out the yarn. There we go. I'm having some trouble getting it to pull on. There we go. Once again, literally everything that can go wrong in a demo is going to go wrong for me. I have no idea what's happening. Oh, yeah, it's connected onto another hook. There. Hopefully you won't have to see me use my fishing hook. I have a little hook here that lets me grab onto yarn if it slips through my fingers and then just drops back onto the bobbin. I need to reach through the hole and then pull it through so that it can actually like get back onto the bobbin properly. Hi, Grayson. So let me go ahead and pull this back out because I got a little bit too much twist in it. There we go. All right. And now we're set up again. Now it's pulling pretty well. It's not perfect, but it's pretty good. I might adjust right here and pull this piece, which is called the mother of all, back a little ways so that the tension's better and so that it pulls on better. There we go. All right. There we go. So what I'm doing with my front hand is I'm slowly letting in twist back here. There are several other different methods of spinning that let the twist in different ways. One is called short draw. There's a couple different ways that you can do it. You can put your hands here and you can do this and pull the fiber this way, or you can do this and pull it out from your hands like that, right? So it's kind of up to your own comfort. If you do choose to spin on a wheel, which you don't have to, spinning wheels are pretty expensive. They tend to be hundreds of dollars, sometimes 1,000 or so. Geez. Um, you can do that, but you can also spend $20 to $30, and you can get a drop spindle. And I actually have another one here of a different kind. Looks like this. All right. And the yarn is all gathered under here as it's completed, and it connects onto the hook just like the other one. So that's how that one works. Now, as far as yarn goes, I've made a lot of different types. I don't know if you saw my yarn wall, but those are all commercial. I think all of them. Most of them are. Some are hand spun. All of the ones I have right here are ones that I've spun recently, though. I have, as of today, spun with wool, alpaca, viscose, which can be basically any plant material. It can be wood pulp, even banana fiber, bamboo. I've spun with dog and cat hair before. That's known as Shangora, and it tends to be blended in with some other fiber, usually also wool. I've spun with cashmere, which comes from goats, and Angora, which comes from rabbits. What I have here is a lot of blends. This one is a good example. So this one is yak and silk, and it kind of has this neat luster to it. I made this in a thread weight as well, but the biggest advantage to different fibers is, well, they cater to your situation. I feel as though the fiber industry in the US is pretty depleted. We don't have a lot of sheep anymore, and that's because they're not subsidized. But for instance, wool is extremely hydrophobic. It is able to resist water for a very long time. And then when it takes on water, eventually, it can absorb, I want to say about 3 times its own weight. So very, very useful for a lot of applications. It is also fire retardant, so it can greatly resist burning. And of course, it's very insulatory. So depending on the type of yarn that you spin, whether you're squishing down the fiber as you go, or whether you're letting in air by long drawing the way that I was, you'll get different effects in your yarn. A woolen yarn is one that looks kind of fuzzy, kind of crazy, but it holds in a lot more air, which means that it's going to insulate a little bit better. A very tight yarn, known as worsted, that's been squished down is going to be a lot stronger, great for hard wearing applications like socks, and sometimes closer to the skin things as well. It really kind of depends on what you'd like. These are not hard and fast rules by any means. You can kind of go crazy, which is one of the benefits to pretty much all fiber arts. Spinning is one of those arts where it used to be seen as simply for production, so people wouldn't really make anything very fancy. A lot of what they would do would be spinning for sales and clothes, and they didn't really make fancy patterns unless it was something they had time for or the money to do, right? Now we can kind of do anything we want, but it wasn't really always like this. In the 70s, there was a very big movement surrounding kind of the removal of art yarn. Art yarn is basically anything that isn't nice and straight and consistent. Art yarn can be lumpy. It can have weird pieces of other types of fiber in it. It can be insane, and it's lovely. But back then, it wasn't really seen as a good thing. It was very much so discouraged. So we're starting to get to the point where more, more and more we see yarn and fiber as an art form. And hopefully someday we'll start seeing more value in different types of fiber as well, just in wool and silk and cotton, the way that we used to see them. So anyway, with that, I can take a couple of questions on pretty much anything.
Great. We have a couple of questions for you. The first question is, would you please pat the dog and tell him he's a good boy?
Grayson, come here. You boy. He's got to do his stretch first.
Yeah.
He's a good boy. Yeah.
Thank you. Our other question is, do the plant fibers behave similarly to the animal fibers?
No, actually they can be very different. So sometimes you can't really let me put it this way. All right, so many plant fibers you are going to need to prepare very specifically. Linen, you need to use water to be able to get flax fibers, which is what linen is made out of, to stick together. Otherwise, it just kind of falls apart, or it might look kind of hairy and it might shed, right? Wool is pretty easy. It catches on itself, right? The texture is extremely different. If you ever pick up a garment that's made with bamboo or viscose, it's going to feel kind of cold, which is lovely if you live in a place like Arizona, right? But inherently, certain types of wool, like those from the merino sheep or the Rambouillet, which is a relative of the merino, are going to be warm to the touch. They're going to reflect back your body heat like really, really well. So it'll be kind of different.
Awesome. Thank you.